and Section 8.3, the integral and comparison tests, estimating sums. In general, it is difficult to find the exact sum of a series. We were able to accomplish this for geometric series in the series 1 over n times n plus 1, because in each of those cases we could find a simple formula for the nth partial sum. But usually it isn't easy to compute the limit as n approaches infinity of the partial sum. Therefore, in this section and the next, we develop tests that enable us to determine whether a series is convergent or divergent without implicitly finding its sum. In some cases, however, our methods will enable us to find good estimates of the sum. In this section, we deal only with series with positive terms, so the partial sums are increasing, in view of the monotonic sequence theorem to decide whether a series is convergent or divergent, and we need to determine whether the partial sums are bounded or not. Now, testing with an integral. Let's investigate the series whose terms are the reciprocals of the squares of the positive integers. The sum as n approaches in 1 to infinity of 1 over n squared is equal to 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and so on. There's no simple formula for the sum of the first n terms, but the computer-generated table of the values given to the right over here suggests that the partial sums are approaching a number near 1.64 as n approaches infinity, and so it looks as if the series is convergent. So as n increases from 5 to 5,000, in a table you can see it's approaching 1.64. Now we can confirm this impression with a geometric argument. Figure 1 shows the curve y equals 1 over x squared and rectangles that lie below the curve. The base of each rectangle is an interval of length 1. The height is equal to the value of the function y equals 1 over x squared at the right endpoint of the interval. So the area here is 1 over 1 squared, the area here is 1 over 2 squared, the area here is 1 over 3 squared, and so forth. So the sum of the areas of the rectangles is the following. If we add them all up, then we get the summation of 1 over n squared. Now, if we exclude the first rectangle, the total area of the remaining rectangles is smaller than the area under the curve y equals 1 over x squared for x is greater than or equal to 1, which is the value of the integral from 1 to infinity of 1 over x squared dx. Now, back in section 5.10, we discovered that this improper integral is convergent and has value 1. So the picture shows that all the partial sums are less than 1 over 1 squared plus the integral that goes from 1 to infinity of 1 over x squared dx, which is equal to 2. Thus, the partial sums are bounded and the series converges. The sum of the series, the limit of the partial sums, is also less than 2. Now, the exact sum of this series was found by the Swiss mathematician Leonhard Euler to be pi squared divided by 6, but the proof of this fact is beyond the scope of this book. Now let's look at the series. We have 1 over the square root of n, which would equal 1 over the square root of 1 plus 1 over the square root of 2 plus 1 over the square root of 3. And you can see over on a table here, as n is 5 goes to 5,000, you can see what's happening with those particular numbers. Now the tables of those values suggest that the partial sums aren't approaching a finite number. So we suspect that the given series may be divergent. Again, we use a picture for confirmation. So in figure 2, we see the curve y equals 1 over the square root of x, but this time we use rectangles whose tops lie above the curve. So here we have the area 1 over the square root of 1, 1 over the square root of 2. So the base of each rectangle is an interval length of 1. The height is equal to the value of the function y equals 1 over the square root of x at the left endpoint of the interval. So the sum of the areas of all the rectangles is equal to the summation of n is equal to 1 to infinity of 1 over the square root of n. This total area is greater than the area under the curve y equals 1 over the square root of x, for x being greater than or equal to 1. which is equal to the integral from 1 to infinity of 1 over the square root of x dx. But we know from section 5.10 that this improper integral is divergent. So in other words, the area under the curve is infinite. So the sum of the series must be infinite, and that is, the series is convergent. The same sort of geometric reasoning that we use for these two series can be used to prove the following test. So the integral test. So suppose that a function is continuous, positive decreasing function on the interval from 1 to infinity, and we can see that the sequence is equal to f of n. Then the series, the summation from n is equal to 1 to infinity of a sub n, is convergent if and only if the improper integral going from 1 to infinity of the function dx is convergent. So in other words, if it goes from 1 to infinity of that function is convergent, then we can say that the series is convergent. If the integral from 1 to infinity of that function is divergent, then we can say that the series is divergent. Now also note that when we use the integral test, it is not necessary to start the series or the integral at n is equal to 1. So for instance, in testing the series 1 over n minus 3 squared, we're starting at n is equal to 4, we would use the integral going from 4 to infinity of 1 over x minus 3 squared dx. And also, it is not necessary that the function be always decreasing. What is important is that f be ultimately decreasing, that is, decreasing for x larger than some number n. Then the series, as n approaches that capital N, is convergent. So therefore, that series is convergent by note 4 of section 8.2.